Okay, welcome to Chapter 10, Section 2. We're going to do operations on functions. We're going to start with addition and subtraction. We could do multiplication and division as well. They follow exactly the pattern you'd expect. So when we talk about adding functions, the way we'd write that in function notation is f plus g of x. And we can expand that and write that simply as f of x plus g of x. Same thing for subtraction. When you subtract functions, you subtract what they're equal to. So nice definitions for that. What's exciting about functions is we get a whole new operation called composition. So that's where we're headed. So let's look at this first example. We've got two functions given with two different names. So we've got f and g. So f of x says that you're supposed to take that input x, square it, and add 1. G of x says that you take the input x, multiply it by 2, and then subtract 3. So the first thing that we're asked to do is find f plus g of x. So to do that, we're going to add f of x plus g of x. So here is x squared plus 1. Being added to 2x minus 3. And that's simply a matter of combining like terms. So the x squared comes first. We've got two constant terms, the 1 and the negative 3. They combine to negative 2, and of course our linear term is 2x. Subtraction in the next example means that we might have to distribute. We're subtracting f of x from both sides, from g. And then we're plugging in a 2. So it looks like we've got 2x minus 3, there's our g, and we're subtracting, so we've got parentheses to say that we're subtracting the x squared minus 1. And then we do that, the negative sign attaches itself to the x squared, it changes the sign on the 1, and we get negative x squared plus 2x. And then we are supposed to substitute 2 into that, so that'll mean squaring 2. 2 squared is 4, that changes its sign to negative 4. 2 times 2 is 4, so those go away and leave us with negative 4. Composite functions is where we're heading. So take a look at this. Suppose you've got two coupons. One allows you to take $10 off the price of a purchase, while the other allows you to take 10% off the price of a purchase. Now the purpose of this example is to show that composition is not commutative. In other words, order matters. So we'll get a better deal when we use the coupons in one order versus another order. Assuming we can use them both. So we're going to let f of x be the rule that says take $10 off the price of a purchase. So there's f of x. So whatever the price of that purchase is, we reduce it by 10. G of x is going to be the rule that says take 10% off the price of a purchase. Well, that means that we're paying the other 90%, so that's 0.9 times x. So if we're allowed to use both, the question is, does the order in which you use the coupons matter? So our first way of approaching this question might be to see what would happen if we used the $10 coupon first and then the 10% coupon. So what is that asking us? That's asking us to do function composition. Now, one of the nice things about using parentheses for function composition is that it looks like grouping symbols. In other words, it looks like we start with the $100 purchase, and then we do f, the function called f, so that would be subtracting 10, and then we do g. Notice that that's the way we do things inside of parentheses. We work from inside out. Now, if you take another look at that, it means that we're doing f before g, which is different from the order that we read and write in. But if you focus on those parentheses and you think of them like grouping symbols, and the emphasis is on the analogy there, remember that's function notation, we're going to do the f first and then the g. So when we take that $100 and we do f first, that says to subtract 10 from 100. We haven't done g yet. We're working from inside out. Of course, 100 minus 10 is 90. So we're taking g of 90. And when we do that, we're going to be multiplying 90 by 0.9. We pay the 90% that isn't covered by the coupon. And that means that we're paying $91. So then the question becomes, what if we did this in the other order? What if we used the 10% off coupon first and then the $10 off coupon? So now we are doing G first, and we're putting G inside of F. And that's exactly what this looks like. I mean, you can say inside because one function is inside the other. That is, G is happening first. So for $100 purchase, we want to see what that means. So we're going to plug $100 into G and then plug that into F. So the first thing, of course, is to apply G to 100. So there's G. G says to multiply the input by 0.9. That input is 100. 90% of 100 is 90. We're doing that arithmetic inside the argument of F. We're now going to apply F. We're going to say, what is F of 90? And of course, F of 90 says to subtract 10, and 10 less than 90 is 80. Now, take a look. These are two different numbers. In the first case, we paid $81, and in this case, we're paying $80. So kind of perhaps not what you'd expect. Now take a look at these rules. When I take 90% of that $10 off, I'm left with 9. So notice that when we do G of F of X, we're subtracting 9. But when we do F of G of X, we're actually subtracting 10 because we have taken the $10 off after. So which is better? Well, I think it's pretty clear that it's better to take the $10 off after instead of taking it first. When you take the $10 off first, then you're only getting 90% of that discount. So it's better to use the 10% off coupon first and then the $10 off coupon. So looking back at that, you can see that you work inside of parentheses, inside of functions first, and from then you work outside. And that looks kind of strange. It looks like we're working from right to left, which is of course opposite the order that we read and write in. Now we can use composition of functions with the notation that we've got already. That is f of g of x, or we can write it in a different way. This circle notation is also read f of g of x. But of course, notice that there's parentheses around the function now. We're saying that we're composing those functions. And we can compose in the other order as well. Here's g of f of x, and we can write that with this composition notation as well, that little circle between the g and the f. So here we're going to look at some numeric examples, and we're going to convince ourselves that what we are doing is g, then f, and when we do that, it's the same thing as doing g of f of x. So here is some arithmetic. Let's start with a number. Let's put 3 into the function called g. So above this table, you can see what g's definition is. It says to add 1. So our output will be 4. Now, if we put that output as input into f, we could say that the input into f is now 4. Well, f says to multiply that input 4 by 3. Well, that gives us an output of 12. Now, let's see if that's the same thing as f of g of x. In other words, if we really are just doing g and making the output of g the input for f. So first off, let's compute what that equals. So it says to take the input g of x, that's x plus 1, and make that the input for f. That means to multiply it by 3. So 3 times the sum of x and 1. So let's do that again with the input of 3. So 3 plus 1 is 4. 4 times 3 is 12. So f of g of x is the same thing as making the output of g the input for f. Let's do another numeric example. So for example, let's start with 0. If we put 0 into g, 0 plus 1 is 1. So our output is 1. If we now make that output from g the input for f, we're saying that we're putting 1 into f. Well, f says to multiply by 3. 1 times 3 is 3. Now let's check out the rule again. Let's start with 0. Let's put a 0 into f of g of x. It says to add 1. That's 1. Multiply by 3. That's 3. We get the same output from f of g of x as we get from putting the output from g into the input for f. Now let's look at this with algebraic symbols. So let's put an x into g. Well, g says to add 1, so that means we're adding 1 to x. There's x plus 1. We're now going to make that the input into f, so there's x plus 1 being put into f. That's going to multiply it by 3. And notice that's exactly what the rule f of g of x does. It takes the input x and adds 1 and then multiplies that by 3. So the exact same thing. Now let's look at several examples where we are using 3 different functions, and we're going to compose them in different orders. So this first question asks us to find j of k of x. So the first thing we're going to do is we're going to look up the rule for k. And it says that k is 3x minus 2. So we're going to take 3x minus 2, and we're going to put that into j. So there's j of 3x minus 2. Take a second right now to remind yourself that that j is a function, and those parentheses are function parentheses. What that's asking us to do now is to take 3x minus 2 and make that the input for the rule called j. So we look up the rule called j. Here it is. It says that j takes the input, squares it, and adds 4. So we're supposed to take that input, square it, and add 4. Now we can do a little bit better than that. We can actually square 3x minus 2 and then combine those terms. So when we do that, square, double square, 3x times 3x is 9x squared. Negative 2 times negative 2 is 4. And then the double of the product, 3x times negative 2, and then doubled is negative 12x. And of course, don't forget that plus 4. When we combine those constant terms, we get a plus 8 there. So there's j of k of x. So let's do another one. The next question asks us to find k of j of x. Now, notice that this is not the question that we just did. The question that we just did is j of k of x. So this asks us to look up what j is. So we look for the rule j. There's the rule j, x squared plus 4. We're going to plug x squared plus 4 into the rule for k. So it says k of x squared plus 4. Remember that k is a function. We're now going to look up the rule for k. K is 3x minus 2. So we're going to take the input x squared plus 4. We're going to multiply it by 3 and then subtract 2. So here's what we get. We multiply it by 3 and we subtract 2. Now we can distribute that 3, and we probably should, just to clean up this answer. So there's 3x squared plus 12. And of course we can combine the two constant terms. The next question asks us what j of m of x is. So we're going to do that in exactly the way we've been doing. We're going to plug m into j. So there's the rule for m, x plus 2 over 3. I'm going to plug that into the rule for j. J says to square the input and then add 4. Now those parentheses say that we're squaring both the numerator and the denominator. So that's going to give us a 9 downstairs and that plus 4. We could clean that up a little bit more, but I think that's an elegant enough way of writing that. Now at this point you may be getting tired of this. You've seen 2 questions that look very similar, but the order in which we compose matters. The first 2 questions have very different answers. So at this point you may be saying, okay, there is really no structure here. This next example is meant to foreshadow the next section, and it's meant to show that there is a lot of structure here. In fact, k and m are very unique functions when compared one to the other. What I mean by that is, if we take m and we plug it into k, what do we expect to get? Well, so far you might be saying, okay, we're going to take the definition of m, which is x plus 2 over 3, and we're going to substitute that into the function k. Now, when we do that, notice that it looks like it's saying the same thing or saying the same thing twice. Take a look at those two 3's. They're about to cancel. The 3 upstairs and 3 downstairs, yeah, those 3's are definitely going to cancel. And after that, the 2's are going to cancel. Plus 2 minus 2. This is showing that there's a lot more structure here than these first 3 examples might lead you to believe. In fact, when you look at the next thing that happens, after the 3's cancel, all we've got is x plus 2 minus 2, and of course, plus 2 minus 2 gives us x. K and m are very special. They're a pair of function called inverse functions. One is the inverse of the other. Now I want you to take a few seconds and just look at k and m and notice that they're the inverse operations in the opposite order. Well, that's the definition of undoing. So whatever one does, the other undoes. So k says to take the input, multiply it by 3, and then subtract 2. M says to take the input, add 2, and then divide by 3. Boy, that should sound very familiar to us. That's exactly how we solve an equation. We undo what was done to the input. So looking back at this example, k of m of x is a function and its inverse. And we can see that when you do something and then immediately undo what you did, you're left with x. In other words, our input started as x. That was the argument of our innermost function. And it ended up with an x at the end. In other words, nothing really changed here. An x became an x. K and m are inverse functions, the topic of our next section.